I think we'll go ahead and get started. ISD would like to welcome you to this month's e-seminar entitled Rubber Expansion Joints from Basic Application to Advanced Solutions. We do have one housekeeping item. We will hold questions until the end of the presentation, and as you think of them, please enter them into the chat box. We will ensure we have enough time at the end of the program to answer all of your questions. I'd like to introduce our presenter, Lloyd Aronson, President of General Rubber Corporation, which many of you know. Lloyd is a licensed engineer with over 30 years of experience in rubber expansion joint development and application. He's also the author of numerous articles on the design and application of performance rubber expansion joints, and he's held numerous terms and positions as FSA Division Chair and Technical Committee Chair, as well as currently holding a seat on their board. We have a number of learning objectives for this particular webinar. The first is that by the end of the session, you should be able to, you should understand the features and benefits of a performance rubber expansion joint design. Should understand how to apply both restrained and unrestrained expansion joints arrangements effectively. You should also, at the same time, be able to identify the source of damaging pipe stresses and the consequences of neglecting some of them. You'll recognize system optimization with both a reduced footprint and energy consumption. You'll learn how to minimize loads on piping, equipment, and support structure, develop a plant reliability and efficiency program, and last, incorporate a condition-based preventive maintenance program. So without further ado, I'll turn it over to Lloyd for the presentation.
Thank you, Joanna. It is my pleasure to present on rubber expansion joints, and I hope you all find it informative and we meet these learning objectives. I will focus on system design and optimization. I'll also review system reliability and efficiency. You may remember we did a presentation about a year ago on system reliability and efficiency, but it's worth a review at this point. So for system design and optimization, owners and pipe stress engineers desire greater system optimization that includes higher reliability, improved energy efficiency, a smaller system footprint, lower construction cost, modular construction, and with less support structure. Utilizing performance rubber expansion joints can achieve these goals by reducing the need for cumbersome main anchors, numerous guides, and/or rigid pipe loops. Functionally, this is achieved with the rubber expansion joint's ability to accept damaging nozzle loads and pipe stresses and replace them with the rubber expansion joint's low stiffness and high movement capability. A relatively simple concept, but one that requires some examples and further discussion to be made clear. It is good to look at the sources of nozzle loads and pipe stresses, and they are installation misalignment pipe strain, thermal expansion and contraction reaction forces, shock and vibration loads, ground settlement and other external displacement forces, and pressure thrust forces. We will look at each of these one by one, and for misalignment pipe strain, we can visualize this. If the misalignment is small or the piping is flexible in the direction of misalignment, the loads and stresses will be low. If the misalignment is large and the piping is rigid, then most certainly the loads and stresses will be high. Rubber expansion joints absorb misalignment. We will explain later how a performance rubber expansion joint with its greater movement capability and lower spring rates does this better than a non-performance joint. Thermal contraction, thermal expansion and contraction reaction forces. Again, we can visualize this. The pipe expands and contracts. If the thermal movement in the pipeline is small, or the piping is flexible in the direction of thermal movements, the loads and stresses will be low. If the thermal movements are large and the piping is rigid, then most certainly the loads and stresses will be high. Again, rubber expansion joints absorb thermal movements. And again, a performance expansion joint will do this that much better. For shock and vibration, if the piping is flexible and not in resonance with the vibration source, the loads and stresses will be low. But if the piping is rigid and in resonance with the vibration, then most certainly the loads and stresses would be high, and rubber expansion joints absorb shock and vibration. And yes, a performance expansion joint will do this that much better. External displacement forces. This includes ground settlement, seismic events, wind and snow loads, to name a few. If the displacement is small, or the piping is flexible in the direction of displacement, the loads and stresses are low. But if the displacement is large and the piping is rigid in that direction, then the stresses will be high. So rubber expansion joints absorb pipe displacements, and yes, a performance EJ will do this that much better. All of these previous stresses have been simply absorbed by the expansion joint, its flexibility and its movement capability. And that represents a significant product benefit. And one that does a good job. Pressure thrust force is not something that can be absorbed by the expansion joint and must be restrained either by system main anchors or by control units. So while it's a primary source of pipe stress, it cannot be simply absorbed into the expansion joint. So, and it's important to recognize that when we put control units on, that the expansion joint now lacks axial flexibility. And we'll illustrate this point more clearly in the coming slides. So now we ask, is any one source of load or stresses more damaging than another? The answer is no. Each source independently has the potential to exceed allowable nozzle loads and pipe stresses. So each one needs to be looked at independently. So we have just shown that the primary features and benefits of rubber expansion joints include absorbing all directional movement, reducing noise and vibration, compensating for misalignment, relieving pipe and anchor stresses, but it is also good to recognize that they have a cycle life in the tens of millions, provides access to piping equipment, and have superior chemical and abrasion resistance. As an illustration, we can see that the product truly has all directional movement in a compact body. Illustrating alternative piping solutions is another good way to make applications more clear. In this illustration, we have 4 examples of 36-inch diameter pipe. It's drawn to go over a 100-foot length. It operates at 90 psi and has an anticipated change in temperature of 100 degrees. So for this application, the piping is going to move 0.8 inches over that change in temperature, and there's nothing we can do about it. We have to design that as allowable movement. So the first example is using in solution 1, uses traditional expansion joints with numerous guides and main anchors. So the rubber expansion joint absorbs the thermal movement and the anchors hold back the pressure thrust force. In solution 2, and you can see that there's an end load at the end is 92,000 pounds. Essentially, that is the pressure thrust force in the system, a relatively high force, but lower than if you didn't accommodate for the thermal movements. The solution 2 has a hard pipe loop, and while that piping holds back the pressure thrust force, and there's no pressure thrust force on the ends because the allowable pipe stress is high, it still has 100,000, more or less, 1,000 pounds of force on the ends. Sometimes the support structure and adjacent equipment cannot handle either one of solution 1 or solution 2's forces, even though the piping is within allowable stress. So solution 3 and 4 come into play, where you can directly absorb the axial movement and hold back the pressure thrust force with an inline pressure balance joint, and the end loads become 4,500 pounds, or you put a much smaller flexible U with 2 universal joints, and that has an end load of a little over 2,000 pounds. So each of these solutions are designed within allowable pipe stress, however, each with very different end loads, energy consumption, and space requirements, as well as construction cost. In a review of our product, we manufacture expansion joints from 1 inch to 12 feet in diameter, pressures exceeding 300 psi, temperature range up to 400 degrees Fahrenheit. In almost all cases, we build in large all-directional movement with low spring rate or stiffness. So what is a performance rubber expansion joint? It utilizes tire cord at a bias ply to optimize directional strength and number of plies. Performance benefits includes reduced body thickness and weight, greater movements, lower stiffness or spring rate, and a larger flange sealing area for zero leakage. Additionally, tire cord is coated with a resorcinol formaldehyde latex, RFL, and that's developed by the tire industry to prevent delamination. You'll not find delamination in a modern car tire, and you will not find it with a performance rubber expansion joint. Materials constructions include all of the performance materials, including EPDM and neoprene, and it goes through food grade and Viton and reinforced with polyester and Kevlar reinforcements, to name a few. So we'd like to look at unrestrained rubber expansion joints at first, and they can take several arrangements. The first and simplest is a single wide arch with large all-directional movements and low stiffness. We're going to use stiffness and spring rate as a kind of interchangeable term. But the dynamic here is that when you use a double arch joint, you have twice the movement capability and half the spring rate of a single arch. A 3 arch has 3 times the movement and 1/3 the spring rate, and a 4 arch has 4 times the movement and 1/4 the spring rate. So the design play here is you match the movement capability on your how much the pipe is going to move, and you match up the spring rate or stiffness according to the end loads that you can withstand. So we talked about control units, and they can be used as limit rods and tie rods. Limit rods have a gap between the nut and the gusset plate. Tie rods have no gap. It's basically finger tight. And they are both designed for the internal pressure thrust force in the piping system. Rubber expansion joints are completely versatile. Reducer rubber expansion joints are an economical way of combining and reducing pipe fitting with an expansion joint. Additionally, the center line of the 2 different integral flange diameters can be manufactured as concentric, eccentric, or to a custom offset. They can be designed as lightweight with fewer plies for greater movements and lower spring rate, as high pressure with additional plies and additional steel reinforcement. They can be designed as high temperature by using EPDM, Viton, and a Kevlar fabric reinforcement. Additionally, they can be designed with built-in lateral and angular offsets, respectively, to accommodate non-standard field conditions. They provide ease of installation without compromising any of the performance capabilities of the rubber expansion joint. And that brings us to restrained rubber expansion joints. Restrained joints hold back pressure thrust force and have movements in select directions. We have a universal tied expansion joint, a hinged rubber expansion joint, and a gimbal rubber expansion joints. We also have some advanced restrained rubber expansion joints, and they include inline pressure balanced rubber expansion joints, elbow pressure balanced rubber expansion joints, and dismantling rubber expansion joints. So for applications, we'll first look at the unrestrained expansion joint system. An unrestrained rubber expansion joints represents the simplest and most cost-effective solution for absorbing axial movement in a piping system equipped with main anchors and numerous guides at specific spacing. Common features and benefits of rubber expansion joints are achieved, and unrestrained expansion joints provide the above given the support structure and adjacent equipment do not have load limitations. Again, remember that the four sources of pipe strain that the joint absorbs, the fifth one is pressure thrust force. So in this case, it's doing 4 out of 5 stress relieving jobs, and you have to rely on the system's anchors to hold back that pressure thrust force, which is the fifth source of stress. And the economic benefit of this arrangement over rigid pipe loops includes a smaller footprint and improved energy efficiency. So this is what an unrestrained expansion joint arrangement looks like. Notice here the main anchors and numerous guides that must be used to hold back the pressure thrust force. And as an illustration, functionally, the expansion joint is directly absorbing axial thermal movement while the anchors restrain the pressure thrust force. And this is the one side, but the other side would have an anchor of equal strength. Next, we'll look at applications utilizing restrained rubber expansion joints. And restrained rubber expansion joints can be used to absorb all directional pipe movements while restraining pressure thrust forces and other external loads. The pressure thrust force in these designs are often self-restrained, allowing for intermediate anchors and far fewer guides to be used. These designs are extremely helpful when designing with space or structural limitations, as well as with load limitations on piping and equipment. Common features and benefits of expansion joints are achieved, and the economic benefit of this approach includes far fewer anchors and guides, resulting in an even smaller footprint and greater energy efficiency and reduced construction costs. So the first restrained arrangement we'll talk about is a universal restrained. Notice here the reduction in anchor size and the number of guides due to the restraint being part of the expansion joint. Functionally, the expansion joint is indirectly absorbing the axial thermal movement in the long pipeline by taking advantage of a change in pipe direction and accepting it as lateral movement at the expansion joint. For the hinged restrained expansion joint, notice again here the reduction in anchor size, the number of guides due to the restraint being part of the hinge assembly. And again, functionally, the pair of hinges are indirectly absorbing the axial thermal movement in the long piping line by taking advantage of a change in pipe direction and accepting it as lateral movement in a single plane. I hope you can visualize there that the hinge is pinned, so there is no extension happening at the direct extension happening at the joint, so it's holding the pressure thrust force in the pipe while moving in that angular and lateral direction. For the gimbal restrained expansion joint, notice once again the reduction in anchor size and the number of guides due to the restraint being part of the gimbal assembly. Functionally, the pair of gimbals are indirectly absorbing the axial thermal movement in the long pipeline by taking advantage of a change in pipe direction and accommodating the lateral movement in multiple planes here. Okay. The next application is an inline pressure balanced expansion joint, and they are the only effective solution for directly absorbing large axial thermal movement while continually self-restraining the pressure thrust force. They are commonly used when support structure and/or adjacent equipment have load limitations and no change of direction can be utilized. So this is it's an interesting arrangement. The interconnection of tie rods here help it to be self-restraining. At the same time, it's allowing for axial movement. A very interesting design and solution for a very specific application. Next, we have an application for elbow pressure balance, similar to the inline pressure balance. They absorb all directional movements while continually self-restraining the pressure thrust force in the system. And these expansion joints are commonly used when the support structure and adjacent equipment have load limitations, but you can take advantage of a change in pipe direction. So we have so far 5 restrained arrangements we talked about, and 4 out of the 5 require a change in pipe direction to accommodate the thermal, the stress relieving. And the one joint, the inline pressure balance, being the only one that can stay in line with the thermal movements and absorb those movements. Okay, this is the illustration for the elbow pressure balance. So again, an interesting arrangement, holds back the pressure thrust force and allows the pipe to move with thermal expansion. Our last application is our dismantling rubber expansion joint. Dismantling expansion joints are designed for self-retraction, not self-restraint. Well, in addition to self-restraint, but self-retraction to facilitate access to piping and equipment, as well as for unmatched ease of installation and subsequent removal due to its pre-compression capability. Additionally, they function as a universal expansion joint and can absorb the all directional pipe movement. So the illustration on the left is a pre-compression capability, and the illustration on the right is a self-retraction application. The dismantling joint can do both functions. And this is an illustration showing how you can remove the adjacent equipment, retract the joint, and then remove the adjacent equipment with more access to the piping and equipment. Okay, for system design and optimization, here's some conclusions that performance rubber expansion joints, both unrestrained and restrained, can play a significant role in designing an optimal piping system. Each expansion joint arrangement possesses unique characteristics, which makes it particularly suitable for a given application. In many cases, multiple solutions are possible, allowing for an owner's preference, and qualified manufacturers are available for further consult and design and review. So for system reliability and efficiency, I said we were going to review this. It's a pretty extensive review, so I'm going to get right into it. This is the maintenance, repair, and operation side. So owners and maintenance professionals desire piping systems with improved uptime and reliability. Utilizing performance rubber expansion joints can achieve these goals with their rugged construction, high cycle life, and superior chemical and abrasion resistance. We're going to show how implementing a FMEA, that's Failure Modes and Effects Analysis program, with improved assessment of failure modes, as well as conducting plant surveys performed with traditional and advanced inspection methods, can virtually eliminate unplanned downtime. An important point is that rubber expansion joints have some degree of degradation and inherent risk. Rubber expansion joints age over time and degrade, not unlike a car tire or a radiator hose or other rubber components within a car. Stress and temperature accelerates aging, and unchecked degradation can lead to catastrophic failure. Of course, we don't want to discourage the use of rubber expansion joints because systems designed without rubber expansion joints or other pipe stress considerations will lack flexibility and can fail much sooner. So again, the performance expansion joint has this optimal bias ply, reduced body thickness, greater movements, lower stiffness, and a larger flange sealing surface. And you may want to compare that to the non-traditional design, the non-performance design. It's more of a traditional non-performance design, and the body is very thick. You can see the thickness of the body is almost as tall as the arch height. So you have massive amounts of stiffness. So the movements are low, the stiffness is high. It's being used, designed with square woven fabric with low carbon steel reinforcement, a narrow abrupt arch, and no coating on that fabric. So you could see delamination on these designs. Compare that with an EPDM with a thick tube and the polyester tire cord at an optimal bias ply, high tensile steel reinforcement, a wide flowing arch, a thinner body so that flange, if you look at that retaining ring, look how much area that retaining ring has to bite down on that flange and create a seal versus the traditional joint, very narrow sealing area. That's why you see a lot of leaking with the non-performance joints. You won't find that with performance joint. Cross-sectional shows it best. So non-performance designs have higher internal stresses, which accelerate their own aging function. They apply higher stresses to the piping and adjacent equipment by replacing thermal stresses with their own high spring rates. They have limited movement capability and a very narrow installation tolerance and performance limitations, sometimes having maintenance issues and only a 5-year useful life. Performance joints have low internal stresses, which makes it last longer because it's not under higher stress. It applies lower stresses to the piping equipment and replaces the thermal stresses with the low spring rate of the joint. They have greater movement capability, a wider installation tolerance. We could go maybe quarter, 3/8, even half-inch installation tolerance, where the non-performance may be restricted to 1/8 of an inch. Rarely have any maintenance issues, and with a plus 20 years service life. These performance joints can be built to custom field dimensions, reducing installation time and cost, as well as increasing service life. So when you install an offset joint to field dimensions, it has 100% of the performance capabilities of the joint, and the application includes accommodating large ground settlement and pipe and equipment modifications. So traditional and advanced inspection methods can be used to evaluate the condition of the rubber expansion joints, and these include dimensional, visual, physical. We will not be talking about advanced and internal on this presentation. The dimensional inspection, they can reveal critical information on how hard the expansion joint has worked over its life. The information also is used to order a performance replacement joint. So If it has an offset that's measured, it explains why it's maybe under some additional stresses. You use that offset measurement to order a performance expansion joint. And when you do measurements, you should do it in the 4 cardinal flange locations and measure face-to-face, lateral, and torsional offsets. For visual inspections, external cracking indicates potential internal cracking. Delamination is a consequence of utilizing non-performance RFL, non-RFL coated fabrics. Visual blisters indicate a compromised tube and fluid wicking through the fabric reinforcement. Ballooning is even more serious and is a sign of compromised fabric reinforcement. And flanged leakage indicates an insufficient sealing area and is common in non-performance expansion joints. Physical inspection can be done with a Sure-A durometer reading. This you can see the dial gauge in the photo. Very inexpensive tool measuring the hardness of the joint. You can get it for less than $50 on Amazon. And aged rubber is generally harder and more brittle to the touch. You can feel that with your fingernail, but you can put a number attached to that with one of these devices. We can tell you the durometer reading of our joint as it was manufactured, typically around 60 duro. If it gets to 80 and 90 duro, it's normally representing some advanced form of age. So we're going to talk briefly about an FMEA program. That's failure modes and effects analysis, qualifying a process failure risk by considering its cause, effects, and failure mode, providing a risk priority number based on the severity of failure, likelihood of occurrence, and ability to detect, recommending corrective actions and a timeline to reduce system risk, and generating a new risk priority number based on the completion of the recommendations. So it's a simple chart. If you look at the severity of failure and you categorize it as 1, it's inconsequential, and the likelihood of occurrence is very little, and the ability to detect is very easily detectable, you don't have a high risk situation. But on the other hand, if that location, that failure is catastrophic, the occurrence is imminent, and it's unable to detect, you've got a high risk priority number, and you should put a inspection program around that scenario. So what we did is we put together a rubber expansion joint FMEA table. The example table covers rubber expansion joints from the process, all levels of process, including design, installation, operation, retrofit. Failure modes includes cracking, delaminations, blisters, ballooning, leaking flanges, to name a few, and the rubber expansion joint risks are quantified. Corrective actions are recommended and can typically half the original risk priority number. The highlighted failure mode is of body blisters and delamination. So this is what it looks like in the field. Unless you're knowing what you're looking for, those blisters are not obvious. So, once it's identified, we can do this risk priority number, make the recommendations to change it out at the next outage, and then assign a new lower risk priority number. If that's something that your end users are interested in, or any aspect of that, we can work with you to develop it. So for reliability and efficiency, some conclusions: combining a performance rubber expansion joint with traditional and advanced inspection methods can significantly decrease the inherent risk of systems that utilize them. A traditional FMEA program will qualify the reduction of system risks resulting from minimizing the severity of expansion joint failure, the likelihood of occurrence, as well as improving the ability to detect. This permits a transition to a replacement for condition-based maintenance program, departing from the previous calendar-based or run to failure practice. So those are the two areas of application, both new construction and MRO, but going through some qualifications, it's good that manufacturers should be both ISO 9001 and 14001 certified. Manufacturers should be an active member of the Fluid Sealing Association, FSA. The Expansion Joint Piping Technical Handbook is newly revised, filled with industry best practice and performance arrangements. It's also a free download. So go to the FSA website, get your free FSA handbook. If you'd like, one of us could send it to you if you prefer to get it that way. Manufacturers should be an active associate member of the International Sealing Distributor Association, contributing to important industry standards and educational materials. Providing all the rubber expansion joints installed at the AP1000 nuclear plants at VC Sumner and Plant Vogel. That's 120-inch double arch and 108-inch inline pressure balance. Inline pressure balance is on the right. Shown below. This is a good example of experience, and manufacturers should have a compiled list outlining their experience for reference. Manufacturing capabilities should include standard and custom rubber expansion joints in large diameter and or offset arrangements, and they should also be equipped to accommodate several large-scale projects simultaneously. Automated and manual hydro and vacuum testing for all sizes and arrangements, burst testing, third-party witnesses should also be available. Manufacturers, degreed and licensed engineers should provide unique solutions to even the most demanding applications. Engineering solutions should utilize CAD and advanced simulation software to create optimal solutions. Manufacturers should provide on-site plant surveys and inspection, as well as troubleshooting, training, and expedited replacements when needed. And as far as unique services, if you have can facilitate system optimization with reduced footprint and energy consumption, minimize loads on piping, equipment and support structure, reduce material and construction cost, direct engineering support with full comprehension on pipe codes and standards, and a performance rubber expansion joint with advanced restrained and unrestrained designs. That helps with the new construction people. For unique services, a transition to a condition-based predictive maintenance program, an FMEA approach with improved assessment of failure modes, industry best practices, direct training and technical support, plant surveys performed with traditional and advanced inspection methods, and performance replacement rubber expansion joints is a good package when you're servicing the MRO market. So industries and sectors served, manufacturers should include the power, fossil and nuclear, chemical processing, wastewater, mining and mineral processing, paper and pulp processing, steel production, marine and HVAC, to name a few. Okay. From the world's largest common cooling water system, Ras Laffan, in Qatar, to multiple AP1000 nuclear plants such as VC Sumner and Vogel, the manufacturer should collaborate with leading EPCs, that's engineering, procurement, construction firms, and understand the demands of large international new construction projects. Similarly, the manufacturer should have and install capacity across multiple industries and sectors dating back decades and experienced in developing maintenance, repair, and operations MRO solutions. Specifically, this includes providing performance replacement expansion joints and educating the the customer to ensure the continued safe, efficient, and reliability of their plants. The manufacturer should be dedicated to providing technical sales and support to original equipment manufacturers, OEMs, across all essential equipment types and around the world. And regarding resources, a manufacturer should find it important to not only provide performance products, but also enrich their clients with detailed application tools and educational materials to help them make the best and most informed decisions. These resources should include and be easily accessible features and benefits, materials and construction, selection and application, catalogs, data sheets, guideline specifications, installation and maintenance instructions, case studies, application demos, solid model images, flange data, technical articles, as well as frequently asked questions. So, speaking of questions, this is the end, and if anyone has any questions, I'd be happy to try to answer them for them.
Are there any questions for Lloyd from the group? Use your chat feature at the lower part of the page just to type in your question if you have any. Lloyd, I'm not seeing any questions come through from the group.
Okay, the last slide will have my email if you don't know already how to get a hold of me. I think Joanna has a couple other things to say, and then we can leave it on the concluding slide.
Absolutely. We'd like to thank you, Lloyd, for your presentation today. I'm intrigued by rubber inspection joints, so I really did appreciate your presentation. We'd like to thank those of you on the call for your participation. A recording of this session will be available online within the next week or so. We'll also be sending you via an email a link to a short program evaluation. Your feedback is extremely important to us, and we hope that you'll take a couple minutes to complete the evaluation for us. That concludes our presentation. Have a good day and a great weekend. Thank you.
Thank you, Joanna.